Hey everyone, let's talk about columns. Columns are vertical compression members which transmit loads from upper levels to lower levels of the structure and all the way down to the foundation. So when the load is acting at the center of the column, it is said to be concentrically loaded. So for concentrically loaded column, it is subjected to pure axial compression. Since columns are generally subjected to large compressive stress, it is recommended to use high-strength concrete and a small percentage of steel reinforcement. ACI code specifies that the steel ratio of column members should be within 1% to maximum 8%. When the axial load is not acting at the center of the column, it is called to be eccentrically loaded column, and it is under axial compression with bending moment due to the eccentricity. If the bending moment occurs along one axis, it is uniaxially loaded column, and if it occurs about x and y axis, it is called biaxially loaded column. So for columns with large axial load with less bending moment, meaning less or small eccentricity, the failure generally occurs by crushing of concrete. But for columns with relatively small axial load with large bending moment or large eccentricity, the failure generally occurs by yielding of steel. But there can also be an eccentricity which provides a balanced failure condition, wherein the steel yields at the same time the concrete crushes. The eccentricity of the column load is the distance from the load to the plastic centroid of the column. The plastic centroid of a column is the location of the resultant force produced by the steel and concrete. It is the point in the column cross-section through which the resultant column load must pass through to produce a uniform strain at failure. If the column is symmetrical, for example a rectangular column, then the plastic centroid is at its cross-section center. But if it's non-symmetrical, for example an L-shaped column or a T column, then the plastic centroid can be calculated by summing up all the moments produced by the steel and concrete. To design a column subjected to a concentric load, it is a pretty much straightforward process because we can take the applied axial load and assume a steel ratio, and we can calculate the required cross-sectional area of the column. But for columns with eccentric loading, the capacity is a combination of your axial load and the bending moment due to the ECC. And there can be a lot of load to moment combination. That's why the relationship of the axial load and bending moment is usually expressed using a P to M interaction diagram. When a column is subjected to axial compression and bending moment due to eccentricity, the axial load capacity of the column decreases as the bending moment increases. So the column is said to be structurally safe when the applied axial load and bending moment combination are within the usable area of the interaction diagram. I got another video which shows how to do a column interaction diagram. This video shows how to calculate the column capacity at various P to M combination. A column can be categorized as a short column or a long column. A long column is also referred to as a slender column. A short column generally fails by crushing of concrete, while a slender column generally fails by buckling due to the slenderness effect. The buckling of a column is the lateral deflection and is also referred to as the delta. A slender column, when subjected to an eccentric axial load, will not only produce a moment due to eccentricity, but it will also produce a moment due to the lateral deflection delta, and this is called the moment P delta. And because of this, the moment is magnified and thus further reducing the column capacity. For this video, we're going to design a column subjected to pure axial compression or a concentrically loaded column, and perhaps we can touch on a slender column design in another video.